Okay, so let's talk for just a moment about the tests. So I don't do test corrections every time, but we're doing them on this test. You can earn back up to 1/3 of the points that you lost on this test by doing test corrections and getting the problems right. So this is not just a, hey, everybody, you get a third. It's a, you have to work, but you can get a third back if you get all these problems right. In terms of resources you are allowed, it is going to be a little different than the test in that I want you to be able to use your notes in your textbook, but I don't want you to use other people, including each other, and I don't want you to use people in the studio. I need you to sit down with your textbook and your notes and figure out how to do these problems, okay? Let me add one more resource, any of the videos on my YouTube channel, and you will find that some of the sample problems look an awful lot like maybe some on the test that you took, okay? So we're adding to this list. You can use any of my videos, all right? Okay. There's this other note here on the side, and it relates to question 1b, which was that integral of like ln something, ln of 7x, I think. And the reason that I put this, I'm soloing this one out here, is that there were 5 people in this room who happened to know the formula for the integral of ln of x, either had memorized it or just happened to write it on the reference sheet. And by using that formula that they either had memorized or had on the reference sheet, made the problem a lot easier than I wanted it to be. I was intending for us to do integration by parts, and some people lost like all the points because you didn't show me integration by parts. So I was going to offer those 5 people, hey, just do this one to show me you know how to do integration by parts, but then I decided, well, why don't we just let anybody do it? So this is like a separate problem. If you just want to do that to replace that 1b on your test, you can get all the points back on that one, okay? And then 1/3 of everything else. Any questions? Okay, I was going to have this due Monday, but if you have work over the weekend, I don't want to stress you out. So Wednesday at the start of class, okay? Right in the folders. All right. Okay, so yeah, separate paper. And you'll turn back your original test and the separate paper. All right, so today is a little bit unusual in that what was the other day? On Wednesday, we kind of got tripped up a little bit with some massively complicated partial fractions examples and didn't have time to do any trig sub practice. So what we're going to do is spend the first 15 minutes today just doing some trig sub practice. So on page 6 in your packet, right around the middle of the page, you're going to start by reading number 3. And you're going to work through this problem here at the bottom of number 3 with your neighbors. And once you finish that, you're jumping over to 4C. So 3 and 4C. Hopefully in the next 15 minutes, we make a lot of progress on those 2 problems, and then we'll come back together and do the new stuff. Yes?
T's in the answer.
Okay, so let's just talk about this last problem and then we'll move on. So I think most groups had gotten to a place where after we do our substitution, we get to this guy, the integral of secant over tan squared. Secant over tan squared. And for me, my default when I have all kinds of trig functions is to change them to sines and cosines, and maybe I can get them talking to each other if I do that. So we change tan squared to the cosine squared over sine squared, because it's in the bottom. And then secant is really 1 over cosine, so that gives me a cosine in the bottom. And then one of these cosines cancels. And so we're left with this guy right here, cosine over sine squared. And this is a u substitution, because if we let u equal just sine, then the derivative is sitting upstairs. So let's finish this guy and then move on. So this thing becomes equals, all right, so integral of downstairs becomes u squared. The derivative of sine is cosine, so the top is simply du. So finally, an integral that I can handle. And this is several layers removed from the original, right? We did a crazy substitution to get theta. Then we can't even handle theta. Now we're at this other substitution for u, and finally something we can deal with. So this is the integral of u to the minus 2 du, and then the power rule, add 1 to the power, divide by the new power. This is basically the answer, but u is far away from the t that we started with. We just have to work our way back up to t. So this guy equals, let's see. So first I'll write it as a negative 1 over u. And then we're going to change u. What was u? Sine theta. Okay, so negative 1 over sine theta. Okay, and then finally, we don't want theta, we want t. And there's this picture. So sine of theta, if you draw a picture, you can actually get it in kind of a nice form. So if we go all the way back to the very first thing we did, which was t equals sine of theta. No, what do we start with? T equals tangent of theta. That was what we started with. And we know tangent is opposite over adjacent, right? So I can think of a right triangle with a theta in it, where the opposite side is t and the adjacent side is 1. Opposite side is t, adjacent side is 1. And this problem is really asking me to find the sine of theta. And the sine is what over what? Opposite over hypotenuse. So if I can just get my hands on that hypotenuse, then I've got my answer. Opposite over hypotenuse. So we got to figure this guy out with the Pythagorean theorem, right? T squared plus 1 squared and then square root. And so then the sine of theta is really opposite over hypotenuse. So we'll just put that over here and we're done. Negative 1 over, opposite is t, divided by the hypotenuse, square root of t squared plus 1. So then, because it's a 1 over, we'll flip, fine. We'll flip this guy at the end. So there's our answer. Negative square root of t squared plus 1, all divided by t plus c. Okay, so is it a ridiculous answer? Yes, it is ridiculous. But look at the original problem. The original problem said integral of 1 over t squared times the square root of 1 plus t squared. That's a ridiculous thing to try to find an antiderivative of. But somehow we did. And if you go through the process of taking a derivative of our answer, which is going to first involve a quotient rule and then in there a chain rule, and you clean it up, you will get exactly the original integrand, which is pretty wild. All right. So we'll give folks just another moment to copy there, and then when we're ready, we turn a few pages to the new section. That's going to be the whole test, that one question. Yes.
So
yeah. Yes. So yeah, so we use t. So t equals tan theta, right? Okay. And so the question is, can we think of this guy as this angle theta as being in some right triangle? So we're going to invent a right triangle. It's going to have a theta in it. That's there. We're going to build this right triangle so that the tangent of this angle is exactly t, but I think of tangent as a ratio, opposite over adjacent. So I'm going to put it over a 1. And then I'm going to build my right triangle with a t on the opposite side and a 1 on the adjacent side. So we build those two parts so the tangent of theta is exactly t according to this right triangle. Right, like just pulling it out of a hat so that we can then find sine of theta in some nice form. Alex? You can solve for theta. So this is actually a slight change. Yeah, so this is a slight change from the one problem we did last class. You can solve this guy for theta, right? It's inverse tangent of t. And so it is correct. Yeah, and so it is correct to say negative 1 over sine of inverse tangent of t, but it's kind of awkward to deal with sine of inverse tan, and so this is the preferred way to finish the problem. They're both equal. If you graph them on your calculator, you get exactly the same graph. I think I would probably give full credit to sine of inverse tangent of t, but this is the preferred way, just because this is less awkward to deal with. Yeah. Is that a question? Okay. All right. So let's move on to this page right here. 12, page 12. All right, on page 12, daily summary. Let's go to Cameron for the summary. Thank you. So number one says we're going to use left of n and right of n to denote the Riemann sums using n left and right rectangles respectively. So left of n says we're going to use n rectangles, and they're going to be governed by using the left-hand endpoint in each interval. So let's try number two here. It says approximate this integral, 3x squared dx between 1 and 3. Okay, so this is something we can do by hand directly, right? It's easy for us to find an antiderivative, but let's put that on hold and just use rectangles. So we're going to do left of 2 and right of 2. So let's take a look at our picture here. So there's the function 3x squared. What does the 2 represent? Number of rectangles, 2 rectangles. So going between 1 and 3, where are we going to cut it off so that we have exactly 2 rectangles? It's right there in the middle, right? So those are our 2 intervals, from 1 to 2 and from 2 to 3. Same thing in the other picture, 1 to 2 and then 2 to 3. And so the first one, we're going to do left-hand rectangles. So in the interval 1 to 2, which point are we going to use to dictate the height of the rectangle? Is the 1. We're going to use the left-hand endpoint. So that means you go up to there. That's the height of your rectangle. And then we do the same thing between 2 and 3. Which point do we pick? 2. So those are my 2 left-hand rectangles. So with your neighbors, spend like the next 60 seconds. I want you to find the sum of the area of those 2 rectangles, and then I want you to draw 2 right rectangles and again find the sum. Okay, so our left rectangles, I think the area is 15 altogether, is that right? Okay, so just start using the notation to get comfortable with it. So it's not just a plain 15, it's that left of 2 equals 15. If you use 2 left rectangles, you get 15. Right? Just make it a complete sentence by adding that left of 2 equals. And then the same thing for right rectangles here. Anybody have a sum for us on the right rectangles? 46. So I heard 39 and I heard 46. What else do we hear? 34 and a half and 40. How about I just change the question and I say shout out a random number. I got 39 too. Yeah. I got a 12 and a 27. What's that? Oh yeah. Don't approximate. You got to use the 3x squared. Yeah. All right. So 12 and 27. We okay with that? So right of 2 is 39. The real answer, like the exact area, is something between these two, right? One of them is an overestimate, the other is under. Okay, so this is not new. And in fact, this was the last question on the test, basically. And we did really well as a class on this question. So let's move on to number 3. And we're going to do something different. I don't think we've done trapezoids before, right? We've only done rectangles. So let's use n equals 2 trapezoids. And we're going to draw 2 trapezoids in this diagram below. And so we're still going, between 1 and 2, and then between 2 and 3. But when it comes to determining the height, well, you use both points, not just the left point exclusively or the right point exclusively, but both of them. So between 1 and 2, draw a straight line, and you've made your trapezoid. You see it? And then between 2 and 3, another trapezoid. Yeah, lowercase is fine. Okay, so to find the areas of these 2 trapezoids, you're welcome to cut it into a rectangle and a triangle, but let's just use the trapezoid area formula. It's not hard. So here's the formula. Area is half the height times the sum of the 2 bases, where the bases are the parallel sides. So let's try it. Let's label these guys here. How much is the height at 1? All right, so that's a 3, and at 2, the 12, and at 3, that's the 27, right? So those are our 3 bases. And so if we're just looking for using this area formula, all right, so we'll use my notation here. Trap of 2 equals, so it says half the height. How much is the height of the first trapezoid? 1, right, between 1 and 2. So half of the height times the sum of the bases. What plus what? 3 plus 12. That's the area of the first trapezoid. and then plus, and then we do the same thing for the second trapezoid. So half of the height again is 1, and then the bases are 12 and 27. Okay, so let's crunch all this stuff together. Let's see, that's 15 halves plus 39 halves. Is that 54? 39 is these two, right? 27? 10. Yeah, so the antiderivative is the exact answer, right? That's also an approximation. Is it going to be an over or underestimate to the real area? Depends on the curve. For this curve, is it an over or under? It's over, right? Like those, every one of those lines, the diagonal lines we drew, is a little bit above the curve, but it's not going to be over by much. Yeah, so Alex wants us to jump to the activity, so let's do that.
I did that. I came up with 27 exactly. I don't.
No, Alex has a theorem. It's on the next page. So go ahead and work through the activity as far as we can and raise a flag if I can help.